Assalamualaikum and a very good morning to everybody. So today in our class we'll be looking at conduction heat transfer, which is one of the mode of heat transfer other than convection and radiation. So first of all, let us look at the person who actually discovered conduction heat transfer. So he is Jean Baptiste Joseph Fourier. He was a French mathematician and physicist from France. So he is the person who actually discovered conduction heat transfer. So again here, this is just a repetition. Conduction can be defined as transfer of heat from molecule to molecule within a substance. The substance can be solid, liquid or gas. But conduction is most prevalent in solid material. And then conduction can be steady state or unsteady state. Fourier, when he was doing his experiment to find out how conduction happens, he discovered that the rate of heat conduction, you can say it as Q, is proportional to the area perpendicular to the direction of heat transfer, which is, we can call it A. It is proportional to the temperature difference, T2 minus T1. You can see here T2 minus T1, and also it is inversely proportional to the thickness of the wall or pipe or any kind of material. So we can say it is delta X. So based on his observation, he came up with this general equation which is known as Fourier's law. So if I were to rewrite again the equation in the previous slide, we said that Q is proportional to the area of heat transfer times the temperature difference T2 minus T1 over the thickness of the heat transfer delta X. So in order for us to remove this proportionality sign to equal sign, we have to add a constant. Now in this case, Fourier decided to add a constant known as K, is also known as thermal conductivity. So he added this K value. So thermal conductivity is defined as a measure of the ability of a material to conduct heat. So you can see here in example, this figure A, copper has a thermal conductivity of 401, whereas silicon has a thermal conductivity of 148. So we can say that copper has a higher or greater ability to conduct heat as compared to silicon. The second thing he added was the negative sign. So the negative sign in this equation is to ensure that the heat transfer in the positive X direction is positive quantity. So the heat transfer in this direction from left to right, from higher temperature to lower temperature, it is a positive value. So this is a chart showing that different material will have different K value. The range of thermal conductivity of various material at room temperature. So this is the first thing that you need to understand about the value of K. Different material will have a different value of K. A high value of thermal conductivity indicates that the material is a good heat conductor, and a low value indicates that the material is a poor heat conductor or an insulator. So you can see here, if you put here graphene and diamond, you can say they are a very good heat conductor because it has a very high value of K. Whereas air, carbon dioxide, hydrogen, helium, all these things, you can say it's a poor heat conductor or a very good insulator because it has a very low value of K. The second thing is that K is dependent with temperature. Now again, it depends on the type of material that you have. For some material, the variation of the value of K is very significant, whereas for other materials, it is not that significant. So for example, if you look at aluminum oxide, when the temperature is increased from 200 to 1400, you can see that there's a big difference in the value of K. But if you look at silver or gold, the value does not vary that much. So for example, here you can see for copper, if the temperature is 100, you have a value of 482. But when the temperature is increased to 800, the value will go down to 366. The same goes for aluminium. At 100 degrees Celsius, it is 302. The temperature goes up, the value goes down. So in generally, in our normal everyday life and in normal application, conduction will happen in all directions. So that is why we say here conduction in Cartesian coordinate. So when you say Cartesian coordinate, you have to remember it is going to be in X direction, Y direction, and also Z direction. So that is why this is the general equation for conduction heat transfer in Cartesian coordinate. We have dq over dA. Q is our heat transfer. A is the area perpendicular to the direction of heat transfer. K is the thermal conductivity. And then this is the heat transfer in X direction, Y direction, and Z direction. So in our case, we are only going to be looking at X direction. So we can cancel off Y direction and Z direction. So our equation will be similar to the Fourier's law, which is dq over dA is equal to negative k dt over dx. So firstly, we're looking at conduction heat transfer through a plane wall, one layer wall. In order for us to use our Fourier's law, we need to make a few assumptions. The first one is that heat transfer only occurs in one direction. So there is no X, there is no Y and Z direction, only X direction. So we have satisfied this assumption. Second one is that no accumulation of energy in the wall. So there can be no accumulation of heat in the wall. Whatever heat is transferred from here, all heat transfer happens going out from here. So there is no accumulation here. The third thing is that the thermal conductivity values does not vary with temperature. So we say that the K value is a constant. Does not matter whatever the temperature we have, 100 or 1000, it is only dependent on the type of material. It is not dependent on temperature. Okay, so now the next thing that you have to know is that the importance of this negative sign. So I will show you how we get from this equation to this equation and what happens to the negative sign. Where does it go? So let's see, for example, this is the cross-sectional area of one layer wall where the heat transfer is happening from the left hand side to the right hand side. Okay, so I just said left and right. So this is the direction of heat transfer. And then remember our definition of heat transfer can only happen from higher temperature to lower temperature. So we can say here is that T1 is greater than T2. So let us just put a value of T1 here. Let's say it is 100 and our T2 value here is 50 degree. Can be degree Celsius or Kelvin, it doesn't matter. So the general equation of heat transfer, Q is equal to negative Ka dt over dx. Now, in order for us to remove the dt dx, we have to do integration. Now, when you do integration, you'll get something like this. Q is equal to negative Ka integration T2 minus T1 and then over x2 minus x1. Okay, so we can say here is that Q is equal to, now this is where we can remove the negative sign. So I know here from this equation, T2 minus T1, this value is going to give me a negative value. X2 minus X1 is going to give me a positive value, because this is where your X1 is, this is where your X2 is. So usually X2 is greater than X1. So this is okay. A positive value, K value is also a positive value, A value is also a positive value. The only negative value is T2 minus T1. So what I can do is that I integrate this negative sign into the T2 minus T1. So what we'll get is Ka T1 minus T2 over X2 minus X1. So now K value is a positive value, A value is a positive value, T1 minus T2, which is in our case 100 minus 50 is a positive value, and also X2 minus X1 is a positive value. Then you'll get a positive value for your Q. So again we write Q is equal to Ka. Now we put here delta T over delta X. So meaning that your delta T and delta X is the temperature difference. So to make you understand easier, always remember, in order for you to calculate the Q value, your delta T must always be higher value of T. Let's say here is T1 minus the lower value of T, which is T2. The same thing goes for your delta X, must be bigger value of X, which is X2, minus the smaller value of X, which is X1. So if you follow this rule, you will always get a positive value of Q. So that's all for today. If you have any questions, you are more than welcome to contact me.